Well, hello guys. Today we're going to have a look at factorising complex polynomials and solution of polynomial equations. This is a two-part mini-series, I suppose, 4E and 4F. So let's have a look at 4E today, and it will be very illuminating for you, I'm sure. Alright, now we're going to deal with two amazing theorems, okay? The first is the fundamental theorem of algebra. And what this says, ladies and gentlemen, is that a polynomial of degree n can be factorised into n linear factors in C. Now, this looks very, very abstract, but just have a look. This is a polynomial of degree n, okay? And what we've got here is n factors. That's what we've got, n factors, okay? Where, what have we said here? All these a's are complex numbers, which can include reals, of course. Remember that reals are subsets of the complex number set, yeah? And k is a constant. And the second one, big superstar theorem here, is the conjugate root theorem, which says that if we have a polynomial with real coefficients, it must have real coefficients. Every term in the polynomial must have a real coefficient. Then, if a plus bi is a solution, one of the solutions of the equation p of z equals 0, where a and b are real numbers, then, ladies and gentlemen, a minus bi, the complex conjugate, must also be a solution. Now, these two theorems are the superstars of our whole topic in complex numbers, okay? So they deserve star status, yes? Now let's have a look at the first one in a little bit more detail. This is the fundamental theorem of algebra. It's best to show you how this works by just using an example. But it means that whatever the degree of the polynomial, this is also going to be the number of factors of that polynomial. Now here's a nice little simple cubic, okay? Now you could factorise that by using the difference of two cubes, yeah? So you would go like that. This is where you would normally leave this. One linear factor here and an irreducible quadratic if you were dealing with just the kinds of cubics you've dealt with up to the point before you started studying complex numbers. But now, ladies and gentlemen, have a look at this. I'm going to do a magic trick on this quadratic, and I'm going to reduce that now by virtue of beautiful little Mr. I into two linear factors, two more linear factors, which proves this fundamental theorem of algebra. It says that if you have a cubic, you must have three linear factors, okay? So, difference of two cubes, yes, and I've completed the square on the quadratic there, as you can see. Yes? Okay, now watch this next trick. Okay, oh, look at that! This is z plus 1 all squared, that's the z squared plus 2z plus 1, but I've turned the plus 3 into minus 3i squared, because as you know, I squared is minus 1. I know, it's just a very, very nice little magic trick. Now, I have a difference of two squares now, which is not irreducible anymore if you've got it in its complex form, and I'll just rewrite that on the next line like that, okay? And of course it's just a matter of factorising according to our difference of two squares rule for factorising, and you get this, yeah? Okay, see now, you've got three linear factors of that cubic polynomial. That is what this fundamental theorem of algebra says. If you have a polynomial of degree n, then you have n linear factors. Let's go over the screen now, get even more excited. This is the conjugate root theorem. It says that p of z is a polynomial with, if it has real coefficients, right? It has to be real coefficients. All terms have to have real coefficients in this polynomial. Then if this is a solution of the equation pz equals 0, where a and b are reals, then this complex conjugate must also be a solution. So this means, ladies and gentlemen, that if p of z is a polynomial with real coefficients, then if pz equals 0, okay, z will be either real or it will form complex conjugate pairs. That's what this theorem means, and we will test that as we do further examples. If the coefficients are not real, then this theorem does not apply. Absolutely no way known. It does not apply. So don't make the mistake of thinking that it always applies. You have to make sure that the coefficients are real before you factorise using this theorem. Now there's the same example as we used before, except that we've set the polynomial equal to 0. So from the previous example we can see that the coefficients are real. This is what we got when we factorised on the previous screen, and I've just set that equal to 0, and therefore you can see by using the null factor rule that z equals 2, or z equals, okay, look at this, minus 1 plus root 3i, or minus 1 minus root 3i, and ladies and gentlemen, that's real, and these are complex conjugate pairs. Okay, very exciting. Now let's do some examples using this new found knowledge. Okay, we've got A and B here, they're both quadratic, so therefore we would expect, if we're factorising those, we would have 2 linear factors each. So let's just go for it and see what we find. We've got this z squared plus 25, which we can turn into a difference of 2 squares. It's z squared minus 25i squared, as you can see, and we're going to factorise that now as a difference of 2 squares, as you can see there, and there she be, okay? And you can see there are 2 linear factors for this quadratic. And another thing that you can see is that we've got basically complex conjugate pairs for these factors. Yes? 5i and minus 5i are complex conjugates. Yes? Okay. Let's do the next one. We've got 4z squared plus 196. Okay. Common factor. Take out the common factor. Always look for the common factor before you do anything. So there she be. Look at that. Now, what's inside the bracket? We've got z squared plus 49. You know what to do, don't you? With complex numbers, you can turn that into a difference of 2 squares, like that. And there's the next line. So we've got 4 into z minus 7i times z plus 7i, and you can see that we have 2 linear factors for this quadratic of degree 2, and of course these factors represent, if we set that equal to 0, that polynomial, we would get z is 7i or minus 7i, which are complex conjugate pairs because we had real coefficients. Yeah, you're getting used to it now, aren't you? It's great, isn't it?